Hi everyone, this is the continuation of the previous lesson. The learning outcome so far, according to the previous video, was the idea of point charge and also the properties of the field lines. And they are not sufficient because we need to do some quantitative measurements on the electrostatic force. We need to cover that in a law that we call it as the Coulomb's law in the next slide. Now let us pay our attention to the Coulomb's law. Coulomb's law here is a law that will describe the quantity of the force between two or more electrical charges. How strong is the force? We can use this law. And in any way, this is almost the same as the Newton's law of universal gravitation. If you like that, then I'm pretty sure you'll like this as well. So let me review to you the formula. Alright, so Mr. Coulomb, he introduced this Coulomb's law. Let me describe this formula slowly. And yeah, we start with the Fe, small e here, for electrostatic or electric force, is equals to 1 over 4 pi epsilon naught multiplied by Q1 Q2 over R square. Alright, so what is Q1 and Q2? Maybe I start off with this. Q1 and Q2 is referring to the charge of the two objects. Yeah, they must be charged here. And then R square, what does it mean? R square here is distance between two charged objects center to center. So R square, yeah, it's not radius here. Yeah, and then 1 over 4 pi epsilon naught, what is that? I can tell you it is a number because epsilon naught here, it is referring to the electronic constant. I think now if you want to find the textbook, usually we still call it as permittivity of free space. Value here, what, 8.85 to the power minus 12 farad per meter. And 1 over 4 pi epsilon naught, this whole term itself is a constant. And if I'm going to draw out the formula for gravity, you maybe will understand why I say they are pretty much same. So if you remember, this is the formula for gravity. It is difficult for me to write this, so bear with me. R square, yeah. So look carefully in the gravity here, capital G here is a constant, yeah. In any way, same as 1 over 4 pi epsilon naught, they are constant. M1, M2 referring to the magnitude of mass in gravity, and R square here is the distance between them, center to center again. So let me tell you that Coulomb's law is directly proportional to the charge of both particles and inversely proportional to the R square. Having said that, Coulomb's law is obeying inverse square law, pretty much same as the gravity. Alright, so think about it. And one thing that I want to remind you is this: the force of gravity, if you still remember, is always attractive. Not so in Coulomb's law. Coulomb's law here, we have two types of charge, two polarities. We can be having positive and negative, and electric force here can be attractive as well as repulsive. So this is one fundamental difference. Remember, in mass here in gravity, we can only find the positive polarity. Somehow we do not know where is the negative polarity of the mass, and we couldn't find it. Gravity always attractive. Coulomb's law here can be attractive or repulsive. Now let us look into the example on how to utilize the Coulomb's law. So if I give you a question here that asks you what is the electrostatic force between two charges, one is positive 1 millicoulomb, another is negative 2 millicoulomb, if they are placed 5 centimeters away. So how do you utilize this formula? Pretty much it's a direct substitution, and this is a formula. You will have it in the formula sheet. So when you do the substitution, 1 over 4 pi epsilon naught is a constant. You will have it in formula sheet also, and substitute the charge here, 1 millicoulomb and negative 2 millicoulomb over a distance of 5 centimeters square. You can use the calculator and obtain this answer very easily. So Fe is equals to negative 7.2 to the power 6 Newton. Alright, so what does this negative represent? The negative here is representing attractive force. So don't worry about the negative. It is okay for you to put it like that. Or if you're feeling not comfortable with the negative, I want to do something about it, you can also express your answer in terms of this. Fe equals to 7.2 power 6 Newton attractive. Okay. Yep, so over here, one positive, one negative, one positive, one negative, you know that they will be attractive in nature. The negative sign here that you have in your answer is representing that attractive nature. Okay, so that's how you use the formula. And if I want to ask you another question here, something similar, what if you double the charge of the 1 millicoulomb to become 2 millicoulomb? What if you change from positive 1 to positive 2? What is the new answer? Coulomb's law, directly proportional to the charge here. If I change one of it to become twice the number, what is the new answer? It is simply double of the value of negative 7.2 to the power 6. Okay, times 2, and I have my new answer, 1.44 power 7 Newton attractive. So Coulomb's law, Fe is directly proportional to the charge of both objects. By using the same example again, I want to illustrate the effect of the 1 over r square, the inverse square law. So previously we had this simple calculation, the two charges over here, how much is the strength of the force. We have the final answer to be Fe equals to 7.2 power 6 Newton attractive. Now if I want to ask you another question here, what happened if I separate the two charges by a distance of 10 centimeter? Initially it was placed 5 centimeter away, and if I'm now going to separate them by 10 cm away, what would be the new force? Okay, so relationship between 5 cm and 10 cm, you have double the distance. And you still remember the inverse square law, if you double the distance, how would the force change? According to this, and this the inverse square law, F proportional to 1 over r square. If the r here, you make it double, you square it, the force will become how many times weaker? Think about it, give you some time. So what would be a new answer if I separate them by 10 cm? Yeah. So double the distance, the forces shall be weaker by 4 times. So what is my new answer? I can take this number here and 4 times as weak divide by 4 to churn out an answer here to be 1.8 to the power 6 Newton, 4 times as weak. Yeah, it's still attractive, but it is weaker because I double the distance. So if by any way I triple the distance, the force will be weaker by 9 times. If I separate them 10 times as far, then I will have a force 100 times weaker. So that's the idea of the inverse square law in Coulomb's law. Now let me summarize the idea of Coulomb's law. Coulomb's law is used to describe the strength of the electrostatic force. It is given by 1 over 4 pi epsilon naught multiply with the charge of Q1 and Q2. We are talking about two charged objects divided by the distance between them. The force here is directly proportional to the charge of each individual object and inversely proportional to the distance between them squared. Again, let me repeat, it's an inverse square law. 1 over 4 pi epsilon naught, this is a constant, and extra information, sometimes we collectively call them as Coulomb's, let me write down, Coulomb's constant. Yeah, Coulomb's constant, bear with me. Okay, I can just straight away give you a number so that you do not need to waste your time in the exam. Coulomb constant, you can double check with me. The value is 9.00 to the power of 9. You can use them straight away. So check with me. So this Coulomb's constant. Coulomb's law used to calculate the strength of the electric force, be it repulsive or attractive. You're talking about two positive charge, expect repulsion force. A positive and a negative, a dipole, expect attractive force. Alright, so you need to practice on this law. You need to do a lot of practice so that you can apply them properly in the exam. Otherwise, you might just panic in the exam because it's the first time you're doing it. So do practice. Yeah, so do the homework. We'll tell you what you need to do. Please do them and have a nice day.